Alright, let's get started. We begin today's class with this question. You can pause the lecture here to answer this question. Alright, let's take a look at this question. Which of the following reactions would not result in a 50-50 mixture of stereoisomeric products? As we have learned in the last lecture, the only time you will get 50-50 is when your products are enantiomers. That is the only time you'll get a 50-50 mixture. So you're asked which of the reactions will not give a 50-50. It means you're looking for products that are not enantiomers. Alright. So let's take a look at both these reactions. Reaction A, this is the product that is formed. The reaction is taking place across this double bond. You're adding chlorine here, hydrogen here. So let's write the products. You can have the chlorine on the top. That is one product. The other product, you can have the chlorine at the bottom. This part of the molecule will not change. That's not the reaction site. All right. Now, if you take a look at both of this, these are enantiomers. This is the only chiral center in the molecule. This is not chiral because both of these are CH3s. Right? So you will get enantiomers and you will get 50-50 of each of them. So reaction A will generate 50-50 mixture of products. All right. Let's take a look at reaction B. Again, the reaction is taking place across this double bond. You're adding chlorine here and hydrogen here. This part of the molecule where you have the OH attached will not change. That's not the site of the reaction. So let's write the products. That part of the molecule is not changing. You can have the chlorine up at the site of the reaction, or you'll get another product that has the chlorine down. Now let's look at the relationship between both these compounds. In both these compounds, you have two chiral centers. And as you can see, in both these compounds, at this chiral center, you have the same configuration. They only differ at the chiral center that is attached to the chlorine. So both these compounds are diastereomers. Since you are forming diastereomers in reaction B, you will not get 50-50. So the answer to this question is reaction B. All right. So always keep in mind you will get a 50-50 only when you're forming enantiomers as the product. Any other case, you will not get a 50-50. All right. In the last lecture, we looked at this example where if you begin with this alkene and performed hydration through H3O+, the reaction goes to the more stable carbocation and you get OH attached to this carbon in the molecule. The same alkene, if you perform oxymercuration, this reaction does not go through carbocation, so the OH gets attached to the more substituted carbon of the double bond. Right? Now the question to ask is there a reagent that will install an OH group on the less substituted carbon of the double bond? In other words, is there a reaction that will allow you to make this product where the OH is going to the less substituted carbon of the double bond? And that reaction is the hydroboration reaction. It is the anti-Markovnikov addition of OH to the double bond. So the OH is added to the less substituted carbon of the double bond. This reaction, hydroboration, is a syn or cis addition of H and OH to the double bonded carbons. So both H and OH are added on the same side of the double bonded carbon. All right. So let's write down the reaction. Let's say I'm starting off with this alkene. The reagents for hydroboration reaction, step 1 is BH3 THF. I'll show you in a minute what is BH3 THF. The second step in the reaction is hydrogen peroxide along with some sodium hydroxide. The second step is also referred to as oxidation step. Okay. So you need both these steps to perform the hydroboration reaction completely. All right. And as I said, it is a syn addition of H and OH goes to the less substituted carbon of the double bond. Hydrogen goes to the more substituted carbon of the double bond. All right. It's an anti-Markovnikov product. So if I put H down, I also have to put OH down. Syn addition, both on the same side. If H is down, the CH3 group would be on the top. That is one product you will get. The other product you will get is the H and OH up. Because the double bond has equal probability to be attacked from either side, top or bottom. So you will get a racemic mixture. 50% of this enantiomer and 50% of this enantiomer. All right. So let's now look at what is BH3THF. That is the key reagent in this reaction. BH3 is borane. This is the structure of BH3. And as we have learned with boron compounds in chapter 2, they have incomplete octet. Boron forms only 3 bonds, that is 6 electrons. So its exception to the octet rule, it has an incomplete octet. Therefore, boron compounds are good Lewis acids. They can accept a pair of electrons. THF is tetrahydrofuran. It's a commonly used solvent. This is the structure of THF. Tetrahydrofuran. Now this can act as a good Lewis base because you have an atom that has lone pairs. So the Lewis acid will react with the Lewis base. Oxygen will give a pair of electrons to boron. As a result of that, you'll form a bond between boron and oxygen. Oxygen now has 1 lone pair, 3 bonds, formal positive charge. Boron has 4 bonds, formal negative charge. So this complex is the BH3-THF complex. Borane is highly unstable, therefore it is sold as a Lewis acid-base complex with THF. Right? So this is how this reagent is sold. Right. Let's now look at the mechanism for this reaction. I've written the overall reaction here again, and as you can see, I've shown you only one of the enantiomer. You can apply the same mechanism to obtain the other enantiomer. All right. Now the mechanism for this reaction should account for 2 things. First, why is it a syn addition? Why do you get H and OH on the same side? The second thing it should account for is why is that OH gets attached to the less substituted carbon of the double bond, and why does H get attached to the more substituted carbon of the double bond? All right. So let's now write the mechanism for this reaction. Please follow me carefully here. This is your alkene you're beginning with. Here is the double bond. The first step in the reaction is attack of the double bond by BH3. So the double bond is the nucleophile, BH3 is the electrophile. Boron is electron deficient, so it is going to behave as the electrophile. Now the BH3 can approach the double bond from the top or from the bottom with equal probability. I am just showing you the BH3 approaching from the bottom. You can write the same mechanism with BH3 approaching from the top. All right. Now when the BH3 approaches the double bond from the bottom, it can approach it two ways. One way as shown in this picture, where the BH2 is close to the less substituted carbon of the double bond and the hydrogen is towards the more substituted carbon of the double bond. That is one way it can approach. The other way it can approach from bottom is when BH2 is close to the more substituted carbon of the double bond and the hydrogen to the less substituted carbon of the double bond. So these are the two possible transition states you can form. Both of these transition states, the BH3 is coming from the bottom. All that is changing is how it is coming. BH2 towards the less substituted carbon in the top transition state, BH2 towards the more substituted carbon in the bottom transition state. Now as you can see here, when it comes this way, where the BH2 is towards the more substituted carbon, there is steric crowding. Groups are fighting for space. All right? So there is electron repulsion between those two large groups. All right? And therefore this transition state is higher in energy and it is therefore not formed. So the reaction predominantly takes this path, because there is no steric repulsion there when the BH2 goes to the less substituted carbon of the double bond. All right. Now if the reaction takes this path, what you will get as a result is this. BH2 attached to the less substituted carbon of the double bond, hydrogen attached to the more substituted carbon of the double bond. Right? So let's see how we draw the arrows to get to this product. Right? Again, please follow me carefully. The double bond is behaving as the nucleophile. So these electrons from the double bond are going towards boron. Because boron is electron deficient, it is acting as the electrophile. Now these electrons between the boron hydrogen, one of the hydrogen, are going towards this bond formation. Formation of the bond between the carbon and this hydrogen. Right? As a result of that, you will get BH2 on this carbon and hydrogen on this carbon. All right? Now the second step in the reaction converts the BH2 to NaOH. And in this step, there is no change in stereochemistry. Which means if the BH2 is down, OH will be down. All you're doing in the step is converting the BH2 to OH without changing the position. If BH2 is down, you'll get the OH down. If BH2 was up, you'll get the OH up. Right? So the second step does not change the stereochemistry. Right? Now for the second step, I'm not going to go into the detailed mechanism, but if you are interested, please let me know. I can go over the mechanism with you. All right? Now if you take a look at the mechanism we have discussed for hydroboration, the first step is the key step. It decides the outcome of the reaction. Because BH2 goes to the less substituted carbon of the double bond, and that is what in the second step gets converted to OH, the OH is installed on the less substituted carbon of the double bond. Because BH2 and hydrogen go on the same side of the double bond, you get a syn addition of H and OH to the double bonded carbons. Right? So the first step is the key step. It decides the outcome of the reaction. All right? Let's now take some examples of this reaction. Let's say I start off with this alkene. Hydroboration reagents, BH3, THF, step 1, step 2, H2O2, NaOH. Like other reactions we have discussed, if it's a straight chain alkane, you don't need to show in the product bold and dotted. You can just write normal bonds. Right? Hydroboration reaction always gives OH to the less substituted carbon, hydrogen to the more substituted carbon. So if you write the product, this would be the product. Now if you take a look at this product, you have a chiral center here. So you're forming a chiral center in this reaction because you're adding this hydrogen to that carbon. As a result of that, you're generating that chiral center. So you will get a racemic mixture. Both the enantiomers 50-50. Right. Let's take another example. Let's say I'm starting with this alkene. Hydroboration conditions, BH3, THF, step 2, H2O2, NaOH. The reaction is taking place across the double bond, OH to the less substituted carbon, hydrogen to the more substituted carbon. Now because this is a cyclic molecule, make sure you write out clearly the bold and the dotted bonds. All right. If I put the hydrogen dotted, I also have to put the OH dotted. If hydrogen is dotted, the methyl group there would be up. That is one product you'll get. The other product you can get is both the hydrogen and the OH on the top, which means the methyl group at this carbon is at the bottom. Now if you take a look at both these products, you have 3 chiral centers in each one of them. At this chiral center and this chiral center, both the compounds have opposite configuration, but they have the same configuration at this chiral center, because that center is not participating in the reaction. It is there as it is from the beginning in the reactant, right? So these two products are diastereomers, because at least one carbon they have the same configuration. All right. So let's take a couple of questions on hydroboration. Here is the first question for you. You can pause the lecture here for a minute to answer this question. All right, let's take a look at this question. Which of the following products would be produced from hydroboration oxidation of one metal, cyclopentene? So let's first write down what is one metal, cyclopentene. Cyclopentane is a 5-membered ring. Pentene means you have a double bond. Now when you're numbering this ring, you can call any of the double bonded carbons as 1. The other would be position 2. So let's say I call this 1. This would be position 2. Right? At position 1 you have a methyl group. So put a methyl group there. You're performing hydroboration reaction. Second step, H2O2, NaOH. OH goes to the less substituted carbon of the double bond, and hydrogen goes to the more substituted carbon of the double bond. I have not shown you stereochemistry in the products. We are just figuring out the product in this reaction, so you can write it with normal bonds. OH goes here, hydrogen goes to this carbon. Right? So the product you will obtain in this reaction is option E. Right? Here is another question for you on hydroboration. You can pause the lecture here to answer this question. Alright, let's take a look at this question. Which of the following reactions would result in the formation of a secondary alcohol? Secondary alcohol means OH is attached to a secondary carbon. Alright, so let's take a look at both of these reactions. In the first reaction, you're taking this alkene and performing a hydration with H3O+. Hydration with H3O+ always goes through carbocation, right? Hydrogen will go to this carbon of the double bond, the less substituted, Markov-Enikov addition. You'll form a tertiary carbocation, OH will go there. So let's write the product. That's the product you will get in reaction B. Let's look at reaction D. It's a hydroboration reaction. You'll get the anti-Markovnikov product. OH to this carbon, hydrogen to this carbon. So let's write the product. Now if you take a look at both these products, in reaction B, this alcohol is a tertiary alcohol because the carbon bearing the OH is attached to 3 other carbons. In reaction D, the product you get is a secondary alcohol because the carbon bearing the OH is attached to 2 other carbons. Since the question is asking you to identify a secondary alcohol, the answer is reaction D. Right. So key things to keep in mind about hydroboration reaction is always you will get syn addition, which means H and OH on the same side of the double bond. The second thing, OH will go to the less substituted carbon of the double bond. H will go to the more substituted carbon of the double bond. Right. So if we go back to this slide now, you can see starting from the same alkene, based on what reagent you are using, you will get 3 different products. If you perform the hydration by H3O+, it will go through the more stable carbocation. You will get the OH installed on this carbon. If you perform oxymercuration, there is no carbocation rearrangement, but it will always follow the Markovnikov rule. You will get OH on the more substituted carbon of the double bond. If you perform hydroboration oxidation, you will get the OH on the less substituted carbon of the double bond. All right. So that finishes hydration, adding H and OH to the double bonded carbons. All right. The next reaction we're going to take a look is called the reduction of alkenes. Now the process of reduction means it's either addition of hydrogen or removal of oxygen. All right. So in this case, we are looking at adding hydrogen across the double bonded carbons. Right. Now some features about the reduction reaction is that it is a heterogeneous reaction, which means you have more than one phase. Now often when you see reactions taking place in the lab, it will be one phase, it will be homogeneous. You'll have a solvent that is mixing both the reactants and the entire system is homogeneous. All right. Now in reduction of alkenes, the reaction conditions, you have more than one phase. At the bottom of the reaction you will see a solid, as well as on top of that you will see a liquid. So since it is more than one phase, this reaction is referred to be a heterogeneous reaction. All right. It always takes place at the surface of the metal. That is why you have the solid at the bottom, which is the metal. All right. Hydrogen gas is employed in the reaction and it's always used in excess. It's very difficult to control exact moles when one of the reactant is a gas. So therefore it's always used in excess. And this reaction always gives syn addition of hydrogens, meaning both the hydrogens are added on the same side of the double bonded carbons. All right. So let's write down the reaction. Let's say I'm starting with this alkene. The reaction conditions, hydrogen gas. The metal usually used is palladium on carbon. Alcohols are usually used as solvents. Now you can have the hydrogens add from the top of the double bond or from the bottom with equal probability. So let's write down the products. If you put the hydrogen down here, here too the hydrogen is down. The second product you can get is hydrogen up, which means hydrogen here too is up. The metal group is at the bottom. Now if you take a look in both these products, you have only one chiral center. That is the chiral center. And you're going to form 50-50 of both these compounds. You're going to form an equal mixture of enantiomers. Therefore this is a racemic mixture. All right. So let's now take a look why this reaction adds hydrogens on the same side of the double bond. So please follow me carefully here. This reaction happens on the surface of the metal. So here is a picture showing you this reaction mechanism. This is your metal surface. In this case, palladium. All right. This here is the H2 molecule, the gas. Now, palladium has a very high affinity for hydrogen. So in the presence of palladium, H2 molecule splits up and you form a palladium hydrogen bond. Right. Now, as the alkene approaches the palladium bound to hydrogen, both the hydrogens are added on the same side of the double bonded carbons. Therefore, in the product, you get the hydrogens added on the same side. All right. Let's take another example. Now, anytime you see the 6-membered ring with 3 alternate pi bonds, that is not going to react with H2PDC. Only this double bond will react, right? And that double bond is straight chain, so I can write the product just normally. I don't need to show bold and dotted, right? So always keep in mind, this tolerates these reaction conditions. It will not react. It will stay as it is in the product. All right. Let's take another example. Let's say I'm starting off with this molecule. We just said this arene ring is going to tolerate the reaction conditions. It is not going to react. Similarly, the C double bond O also tolerates these reaction conditions. So the only double bond that will react in this molecule is this double bond. So let's write the product. That is going to stay as it is. The C double bond O is also going to stay as it is. So that will be the product in this reaction. Right? So both C double bond O and the arene will tolerate this reaction conditions. Right? Let's take another example. Let's say I have this alkene. Same reaction conditions. Now, as I mentioned in the previous slide, hydrogen is usually used in excess. So all C double bond Cs in the reactant will get reduced, right? So this molecule has 2 C double bond Cs, both will get reduced and you'll form an alkane. All right. So key points about reduction reaction: it is a heterogeneous reaction. Hydrogen is used in excess. It's always a syn addition of hydrogens to the double bonded carbons. And finally, arene as well as C double bond O will tolerate these reaction conditions. All right. So here is a question for you on reduction reaction. You can pause the lecture here to answer this question. All right, let's take a look at this question. Which of these reactants upon reduction will give this as the product? So let's begin with reactant A. C double bond O will tolerate these conditions. It will remain as it is. This double bond will get reduced to a single bond. Therefore, A will give this product. Similarly, B will also give this product. This double bond will get reduced to single bond. C will also give this product. D will also give this product. Right? So all reactants A, B, C, D will give this product upon reduction. All right. So the answer to this question is all the above. So as you can see, looking at the product, you cannot tell where the double bond was in the reactant. different alkenes could give the same product upon reduction. Right? So that finishes reduction reaction. The next reaction we are going to take a look at is called the Simon-Smith reaction. Now, often in organic chemistry, you will see reactions are named after the scientists who have come up with the reaction. The Simon-Smith reaction results in the formation of a cyclopropane ring. All right. So let's write the reaction. Let's say you start with this alkene. The reaction conditions for Simon-Smith: diiodomethane, CH2I2, in the presence of zinc and copper. Usually the solvent used is ether. Now you can form the cyclopropane ring from the top or from the bottom with equal probability. So let's write both the products. Let's say you form the cyclopropane ring from the top, which means the metal group will be at the bottom. You can also form the cyclopropane ring from the bottom, which means the metal group will be on the top. There is equal probability to form both these products, 50%, 50%. As you can see, both of these are enantiomers, so you will end up with a racemic mixture. So let me show you with the help of the model these two molecules. So here are the two molecules with the cyclopropane ring on the top and at the bottom. So let's take a look at the models. So here is the molecule with cyclopropane ring on the top. So here is the top cyclopropane ring. Hydrogen here is at the bottom. CH3 here is at the bottom, okay, as you can see that, right? And this is your 5-membered ring, all right? So this is one molecule and there is equal probability to form the other. So let's take a look at the model. So this is the cyclopropane ring at the bottom. As you can see, hydrogen is on the top, CH3 here is on the top, the ring is at the bottom, right? Now there's equal probability to form both of this, so you'll get 50% of this and 50% of this, all right? And if you take a look, these two are enantiomers. As you can see, they are non-superimposable mirror images. If you put a mirror here, this is a mirror image of this. Okay, you can see that, right? And they're non-superimposable. If you try to superimpose these two, you can see these groups don't match, all right? So you have equal probability to form both of this, so you will get 50% of this and 50% of this, which means you will end up with a racemic mixture. All right. So let's go back to the slides. Let's now write the mechanism for this reaction. You're starting off with this alkene. Now this combination of reagents, CH2I2, zinc and copper, generate this species. This is the active reagent in this reaction, and this is called a carbene. Carbon with 2 bonds and 1 lone pair is called a carbene. So a carbene is the active reagent in this reaction, right? Now if you calculate the formal charge of this carbon in carbene, you will get the formal charge as 0. Carbon with 2 bonds and 1 lone pair, all right? And if you count the number of electrons on that carbon in carbene, it has 2 bonds, that is 4 electrons, plus 1 lone pair, that's a total of 6 electrons. So a carbene carbon has only 6 electrons. So it's electron deficient, it wants to get to 8. So a carbene is a neutral electrophile because it's searching for electrons to get to 8. right? The nucleophile in the reaction is the alkene. Now this reaction happens entirely in one step, right? So start the arrow from the nucleophile, go towards the electrophile. So those pi electrons are donated to the carbene-carbon. The carbene-carbon now becomes negative charge. That negative charge is donated back to the carbon of the double bond. Now this attack of the carbene on the double bond can happen from the top or from the bottom with equal probability. I'm just showing you the product when the attack happens from the top. So this is the ring. The attack is happening from the top. So you form the cyclopropane ring on the top, and this is your CH2. Because you form the cyclopropane ring on the top, this CH3 is pushed to the bottom, right? So let me break down this mechanism and show you stepwise. Please remember, it's not occurring stepwise. I'm just breaking it down for you to simplify the mechanism, right? This is the carbene-carbon. So draw the arrow from the nucleophile to the electrophile. So as a result of that, you're going to form this. Now this carbon has 3 bonds, 1 lone pair. That's a formal negative charge. Carbon with 8 electrons, 3 bonds is formal negative charge. Now this negative charge you can think is going back to that carbon and forming the bond of the cyclopropane ring. Right? So you can visualize this mechanism like this to simplify it. But keep in mind it is happening in one step. Right? So if you take a look at this reaction, that additional carbon in the cyclopropane ring is coming from the diiodomethane in the reactant. Right? So that CH2 is what is getting installed to form the cyclopropane ring. All right? So let's take some examples of the Simon-Smith reaction. Let's say I start off with this molecule. Reaction conditions: CH2, I2, zinc, copper. Solvent is ether. Okay. Everything else in the molecule will remain the same. You are just going to install to the double bond a cyclopropane ring. Okay. So this CH2 is this CH2. Right? Everything else will remain the same. Right? Let's take another example. Let's say I start off with that molecule, same reaction conditions of Simon-Smith. All right. Now, first thing I want you all to note is the arene ring does not react like a double bond. So all the reactions we are discussing in this chapter are specific for the double bond, a single double bond. All right. So the arene, which is a 6-membered ring that has alternate double bonds, will not react under these conditions. All right. So that will remain as it is. Right. Now, if you take a look, you have a trans alkene. The groups are on the opposite side, CH3 and the arene ring. And that trans geometry will be maintained in the product. So you will form the cyclopropane ring, and the groups, the arene group and the CH3 would be trans, one up, one down, because in the reactant they are trans. Right? So this is one enantiomer you'll form. The other enantiomer you'll form is this. Right? You will get a racemic mixture. So if you're starting off with an alkene that has a trans geometry, the groups in the product will also be trans. Right? If you start off with an alkene that is a cis geometry, the groups in the product will be cis. Again, same reaction conditions. Okay, that's one enantiomer you will form. The other enantiomer is when you have both the groups at the bottom. Okay, so you'll end up with a racemic mixture. So always keep in mind, if you start with trans, you will have a trans relationship. If you start with cis, you will have a cis relationship in the product. All right. So that is about the Simon-Smith reaction. The next reaction, a very similar reaction, is called the epoxidation reaction. Now, before we get into the details of epoxidation, let's first understand what is an epoxide. An epoxide is a three-membered ring containing an oxygen. So this is an epoxide. Now to the epoxide, you can have R groups attached to it, or you can have hydrogens attached to it, or a mix of hydrogens and R groups. All right. So let me show you the structure of an epoxide. So here is the structure of the epoxide. This is the three-membered ring, 2 carbons and 1 oxygen. As you can see, the ring is a very strained ring. All right. Now the epoxide I've shown you has 2 hydrogens and 2 R groups attached to it. All right. So let's now look at the conditions to make the epoxide. Now the reagent used to generate epoxides from alkene is this molecule. This molecule is called metachloroperbenzoic acid, abbreviated as MCPBA. Right? Now these class of molecules are called peroxy acids. Peroxy because they have an OO linkage. If you remember, hydrogen peroxide is H2O2. Right? So this OO linkage is referred to as a peroxy linkage. So these class of molecules that have that linkage are called peroxy acids. Right? The generic formula of peroxy acids is RCOOOH. So whether you see the reagent as MCPBA or this, it means you're looking at the same reaction of epoxidation. All right. So let's write the reaction. Let's say I start off with this alkene, MCPBA, solvent dichloromethane. Product, you'll form an epoxide. Now if you look at the product, you're forming one chiral center as a result of this reaction. So you will get a racemic mixture. At that chiral center, you can have this group up or down. So you will get both of this with equal probability, 50-50. So you will get a racemic mixture. All right. So let's now look at the mechanism for this reaction. This reaction has no reaction intermediates. The reaction occurs in one step. All bonds are broken and formed at the same time. A one-step reaction is also referred to as a concerted reaction. Right? So let's write the mechanism. Let's say I start off with a generic alkene. Let's write the structure of MCPBA. This is the structure of MCPBA. Now please follow carefully how I draw the arrows. Let's say this pi bond in the C double bond O, the pi electrons are donated to pick up a H plus. Let's say those pi electrons pick up a H plus, right? As a result of that, this carbon is losing electrons, so it takes these electrons between the oxygen-oxygen bond. A peroxy linkage is a weak linkage, so that bond is broken easily. You start to form a new pi bond here. As a result of that, this oxygen becomes electrophilic because these electrons are taken away from it. And we know alkenes behave as nucleophiles. So draw the arrow from the carbon-carbon double bond towards that oxygen. As a result of that, one of the carbon in the double bond is going to become positive charge because the pi electrons are going to the oxygen. Now these bonded electrons will go back to that carbon that is positive charge, right? So as a result of that, you will get the epoxide. Right. So as you can see, the entire reaction happens in one step. All right. All the bonds are broken and formed simultaneously. Right. The oxygen in the epoxide is coming from the MCPBA. Okay. That peroxy linkage is weak. It is broken up, and as a result of that, you install the oxygen on the alkene, and the byproduct you get in the reaction is this. Right. So this is the mechanism of epoxidation. Let's now take some examples. Let's say I start off with this alkene, that is trans. I perform epoxidation. Because the relationship between the groups is trans, in the epoxide too, it will remain trans. One up, one down. You will get that molecule as well as you will get this molecule. And as you can see, these are mirror images. They both are chiral. You'll get 50% of each, which means you will get a racemic mixture. Right. If you start with an alkene that had the groups cis, you perform epoxidation, the groups will remain cis. And if you take a look at this compound, you have two chiral centers, which means carbons attached to 4 different groups. However, you have a plane of symmetry. So this is a meso compound. All right. So epoxidation is done in the presence of MCPBA or peroxy acids. It will result in the formation of a 3-membered ring containing oxygen. And that oxygen is coming from the reagent. The carbon in the ring is coming from the double bonded carbons. Now epoxides are very useful compounds because they are highly reactive. Starting from epoxides, you can make several other compounds. Let's take an example. Acid catalyzed ring opening of epoxides. Epoxides are reactive due to ring strain. They always open up trans in the presence of acidified water, resulting in trans 1,2 diols. So let's take an example. Let's say I start off with this epoxide. And I react this with H3O plus, acidified water. For the sake of simplicity, you can write H3O plus as H plus and water. Identify the nucleophile and the electrophile. Electrophile is H plus, nucleophile is the oxygen. It has lone pairs that can be donated. So first step, oxygen gets protonated. right? Oxygen with 3 bonds, 1 lone pair, formal positive charge. Now you have plenty of water floating around that can react to open up this ring. Now if the epoxide is at the top, water will come from the bottom, like we have seen with the dihalogenation and halohydrin formation. So water will go from the bottom you will open up that ring. These electrons will go to oxygen. So here the stereochemistry will not change. It will remain as it is. The reaction is not taking place there. The reaction is taking place at this carbon. At that carbon you will have water at the bottom. Again, water can act as a base. Pluck that proton, give these electrons to oxygen. As a result of that, you will form the diol, trans 1,2 diol. The other product will be H3O+. So as you can see, H3O+ is generated back at the end of the reaction. That's why it is acid catalyzed ring opening, right? Now this molecule is called trans 1,2 diol. The reason being, as you can see, the OH are on the opposite side, so trans. And if you call this carbon bearing the OH as 1, relative to that, the second OH is on carbon number 2. So this is called trans 1,2 diols. So always epoxide will open up trans, right? You'll have 2 OH groups trans once you open up the epoxide with acidified water. All right. So here is a question for you on epoxidation. You can pause the lecture here to answer this question. All right, let's take a look at this question. You're starting off with this molecule. First, you're performing a reaction with MCPBA. MCPBA results in the formation of epoxide. So this is the product you will get upon MCPBA reaction. You can have the epoxide on the top or at the bottom, right? And keep in mind the arene does not react with MCPBA. So it is there as it is in the product, all right? The second step I've given you is acidified water, which means you're opening up that epoxide. And anytime you open up the epoxide, you will get a trans 1,2 diol. OH, trans 1,2. Right? So the product of this reaction would be C. You will never get a cis diol when you open up an epoxide. So you cannot have this as the product. Always epoxides will open trans. The OH will be trans with respect to each other. All right. We'll end today's lecture here. Please make sure you go over the mechanisms we have discussed in today's lecture and let me know if you have any questions. Have a good rest of the day.